Have you ever heard of a star so intense, so unpredictable, and so potentially destructive that NASA literally monitors it 24 hours a day, 7 days a week? No, it's not some distant alien sun in another galaxy, it's our very own sun. That's right, the same star that gives us life is also capable of wreaking havoc on our planet. In today's video, we're diving into why this massive, burning ball of gas keeps NASA and scientists on edge. From solar flares to geomagnetic storms, this is one cosmic entity you don't want to underestimate. Stick around as we explore the 5 reasons why NASA can't take its eyes off the sun. The first reason NASA watches the sun 24/7 is because of solar flares. These are sudden bursts of radiation and energy caused by the tangling, crossing, or reorganizing of magnetic field lines near sunspots. When this happens, enormous amounts of energy are released, enough to power the entire Earth for thousands of years. While the energy doesn't directly reach us in the form of heat or visible destruction, its radiation can severely disrupt communications, satellites, and power grids. Back in 1989, a solar flare knocked out power to 6 million people in Quebec, Canada. Imagine a flare just a bit stronger. It could paralyze modern civilization. That's why satellites like NASA's Solar Dynamics Observatory are constantly watching for these events. The danger is not just theoretical. It's real, it's proven, and it's why the sun is one of the most closely watched objects in the universe. Closely tied to solar flares are coronal mass ejections, or CMEs. Think of these as giant magnetic shock waves that the sun hurls out into space. A CME can carry billions of tons of plasma and magnetic field from the solar corona and shoot it straight toward Earth. If one hits, it can cause massive geomagnetic storms, much worse than solar flares alone. The danger with CMEs is their unpredictability. Unlike the relatively quick burst of a flare, a CME can take hours or even days to reach Earth, but the impact can be long-lasting. Power grid failures, satellite damage, and even increased radiation exposure on planes are all real risks. In 2012, a CME barely missed Earth. Had it hit, experts say the damage could have cost up to $2 trillion in the US alone. That near miss is one of the big reasons NASA never stops watching the sun. Sunspots might just look like little dark blemishes on the sun's surface, but they're actually signs of serious solar activity. These areas are cooler than the surrounding regions and are typically where solar flares and CMEs originate. The more sunspots, the more volatile the sun tends to be. That's why NASA and observatories around the world track sunspot activity religiously. What's really fascinating is that sunspot activity follows an 11-year cycle. Right now, we're moving toward what's known as the solar maximum, where sunspot numbers increase and the likelihood of flares and CMEs also rises. By monitoring sunspots, NASA can somewhat predict solar events before they happen, giving us a critical window of time to protect technology and infrastructure. It's like watching storm clouds form before a hurricane, only this storm is 93 million miles away. If you think solar danger is just a modern concern, think again. In 1859, a massive solar storm known as the Carrington event struck Earth. It was the most powerful geomagnetic storm on record. Telegraph systems across Europe and North America failed, sparked fires, and even shocked operators. The auroras were so strong, they were visible in the Caribbean. If a similar event occurred today, the consequences would be catastrophic. We live in a world that is infinitely more reliant on electronics, satellites, and digital infrastructure. NASA's constant solar surveillance is, in part, a reaction to the terrifying power of events like this. They remind us that the sun, while life-giving, can also be violently destructive. It's not a matter of if it happens again, it's when. Lastly, NASA watches the sun constantly to protect astronauts and spacecraft. Solar radiation, especially during a flare or CME, can be deadly beyond Earth's protective magnetic field. Missions to the Moon, Mars, or even the International Space Station require real-time solar monitoring to ensure crew safety. A sudden spike in radiation can be fatal without warning. Radiation also damages spacecraft systems, causing costly delays and mission failures. In deep space, where there's little atmospheric shielding, one solar burst can shut down communications or fry electronic circuits. By having eyes on the sun at all times, NASA can issue alerts, shift or pause missions, and keep billion-dollar projects and human lives safe. In this way, the sun isn't just a distant ball of fire, it's a real-time threat to everything we put into space. While most people associate climate change with human activity, the sun plays a natural and powerful role in Earth's climate systems. Variations in solar radiation influence weather patterns, ocean currents, and global temperatures. Although these changes are gradual, they're far from insignificant. For example, the Little Ice Age from the 14th to 19th centuries coincided with a period of extremely low sunspot activity known as the Maunder minimum. NASA monitors the sun's total solar irradiance, the amount of energy the Earth receives, using advanced space telescopes. These observations help scientists separate natural solar influences from human-driven climate change. A drop or rise in solar output over years or decades could amplify or dampen climate trends, making accurate solar data essential for climate modeling. If solar activity drops too low, it could lead to cooler temperatures and disrupted growing seasons. If it spikes, it might compound the effects of global warming. This relationship between the sun and climate is yet another reason NASA dedicates billions of dollars and 24/7 eyes on our nearest star. Auroras, those breathtaking waves of color in the polar skies, are more than just a pretty light show. They're direct evidence of the sun's volatile relationship with Earth. These lights form when charged particles from solar winds, or CMEs, collide with Earth's magnetic field and atmosphere, releasing energy as light. While auroras themselves are harmless, the solar storms that cause them are not. They're often signs that Earth is being bombarded by solar radiation. During intense storms, auroras can be seen at latitudes far from the poles, a red flag for space weather scientists. In fact, unusual auroral activity is often one of the first signs of a CME impact. NASA and NOAA monitor these events to predict when and where auroras will appear, and more importantly, to assess potential disruptions to navigation systems, satellites, and electrical grids. So the next time you see a brilliant aurora, just remember, something powerful and potentially dangerous is happening way up in space. Launched in 2018, NASA's Parker Solar Probe is on a groundbreaking mission to touch the sun. It's the closest any man-made object has ever gotten to our star, flying within just a few million miles of its surface. The spacecraft is equipped with state-of-the-art instruments to measure magnetic fields, plasma waves, and solar wind particles directly. Why get so close? Because understanding the sun's outer atmosphere, or corona, is key to predicting its behavior. The corona is where solar flares and CMEs originate, but it remains one of the most mysterious regions of the sun. One strange fact, it's hotter than the sun's surface, a puzzle scientists are still trying to solve. The Parker Solar Probe endures temperatures over 2,500 degrees Fahrenheit and speeds over 430,000 miles per hour. It's revolutionizing our knowledge of how solar energy travels, helping us develop better early warning systems for solar storms. This bold mission underscores just how far NASA will go, literally, to monitor and understand our dangerous star. You may not realize it, but the Earth is constantly bombarded by a stream of charged particles from the sun known as the solar wind. This solar wind flows out in all directions, filling our solar system with a plasma soup of electrons and protons. Though usually gentle, this wind can turn violent during solar storms. The solar wind interacts with Earth's magnetic field, sometimes compressing it and causing geomagnetic disturbances. These interactions can confuse compass readings, disrupt satellite communication, and create radiation hazards for high-altitude flights. In space, the impact is even more significant. It can erode planetary atmospheres, damage spacecraft electronics, and endanger astronauts. NASA tracks the solar wind using satellites like ACE and the Deep Space Climate Observatory, DSCOVR. By measuring changes in the wind's speed, density, and magnetic properties, scientists can forecast potential space weather threats. Even a subtle increase in solar wind activity can serve as a warning of an impending storm, and that's why NASA never stops watching. Heliophysics is the branch of science that studies the sun and its influence on the solar system, especially Earth. It combines solar physics, space weather, and the study of the sun's interaction with planetary environments. NASA's heliophysics division is tasked with one primary goal: to understand and predict the sun's behavior. This field is more than just academic. It has practical, even urgent implications. A single solar event could cripple GPS, black out communication satellites, or even bring global aviation to a halt. By advancing heliophysics research, scientists are developing predictive models that could one day give us hours or even days of warning before a major solar event hits. With dedicated missions like SOHO, STEREO, and the upcoming ESA-NASA Solar Orbiter collaboration, heliophysics is becoming more advanced and data-driven than ever. It's a full-time scientific commitment driven by the understanding that our lives and our tech-driven civilization depend on keeping an eye on the sun. The sun's magnetic field is one of the most complex and dynamic forces in the solar system. Unlike Earth's relatively stable field, the sun's magnetic field flips polarity roughly every 11 years during the solar cycle. North becomes south and vice versa, a cosmic reset that comes with powerful consequences. This magnetic shift can increase solar activity, causing more sunspots, flares, and CMEs. These fluctuations impact everything from satellite operations to astronaut missions. NASA's solar observatories monitor the magnetic field's strength, movement, and structure to understand how it influences space weather. The constant dance of charged particles and twisting magnetic lines is the root of nearly all solar violence. When magnetic loops become tangled and snap, they release massive energy in the form of solar flares or CMEs. Understanding this process is like decoding the sun's heartbeat. And if we can accurately model these changes, we might one day predict solar storms as reliably as we forecast hurricanes. Until then, NASA keeps a constant watch on this ever-changing magnetic beast. Our modern world is built on a network of satellites for communication, weather forecasting, navigation, military use, and more. But every single one of them is vulnerable to the sun. A powerful solar flare or CME can induce electrical currents strong enough to damage or destroy satellite components. Worse, they can knock satellites offline completely. In 2003, during the Halloween solar storms, several satellites suffered malfunctions, and the Japanese ADOS-2 spacecraft was lost entirely. GPS systems became unreliable, and airline communication was disrupted. That wasn't even a worst-case scenario. NASA works with NOAA and other agencies to provide early warnings so satellite operators can power down systems or switch to safe modes. But with over 6,000 satellites in orbit today and thousands more planned, the risk grows every year. It's one more reason NASA must keep its solar monitoring systems active 24/7. One flare in the wrong direction could cost billions and knock out key parts of global infrastructure. It might surprise you to know that solar storms can affect something as common as commercial flights. High-altitude, polar route flights are particularly at risk because Earth's magnetic field offers less protection near the poles. When solar radiation increases during flares or CMEs, the upper atmosphere becomes more charged, increasing radiation exposure for passengers and flight crews. During major solar events, airlines are often forced to reroute flights away from polar regions, which adds time, cost, and fuel usage. Navigation systems and radio communication can also become unreliable, posing safety risks. In 2015, several airlines reported communication blackouts on polar routes during a solar storm. NASA's continuous solar monitoring enables the FAA and airline companies to make quick decisions in these situations. Without that real-time solar data, global air traffic could face unmanageable hazards. The skies aren't just affected by weather down here. Space weather plays a crucial role too. One lesser-known but serious effect of solar activity is how it impacts Earth's thermosphere, the layer of atmosphere where many satellites orbit. During intense solar storms, the thermosphere heats up and expands, increasing atmospheric drag on satellites. This drag can slow satellites down, altering their orbits or pulling them back toward Earth prematurely. This happened in 1979 with the Skylab space station. Increased solar activity caused unexpected drag, and NASA was unable to boost the station's orbit in time. It re-entered Earth's atmosphere and broke up over the Indian Ocean and Australia. Today, with thousands of satellites in low Earth orbit, including mega constellations like Starlink, the stakes are much higher. NASA tracks solar activity and models thermospheric expansion to help satellite operators manage orbital decay and collision risks. The sun doesn't just threaten from afar, its reach extends all the way into low Earth orbit. Solar flares don't just pose a threat to physical equipment, they can directly disrupt radio communication. When a strong flare hits, it releases X-rays and ultraviolet radiation that ionize Earth's upper atmosphere. This can block high-frequency, HF, radio signals used by pilots, ships, and emergency responders. These blackouts can last from minutes to hours, depending on the flare's intensity. In worst-case scenarios, they affect wide regions of the globe. For example, during a major flare in September 2017, NOAA recorded a near-total radio blackout over the Atlantic Ocean. For those in disaster zones, military operations, or on long-distance flights, such communication failures can be critical. That's why NASA uses satellites like GOES and the Solar Dynamics Observatory to issue real-time alerts about incoming solar flares. Quick action can help reroute communication or switch to alternative frequencies. But without constant monitoring, these blackouts would hit us with no warning at all. The sun goes through an approximately 11-year cycle of activity, transitioning between solar minimums, quiet periods, and solar maximums, high activity. During solar maximum, the sun is peppered with sunspots and produces more flares and CMEs. Understanding where we are in this cycle is crucial for planning everything from spacecraft launches to power grid protection. NASA tracks this cycle using data from multiple missions. The current cycle, Solar Cycle 25, is expected to peak around 2025, and early signs show it could be more intense than previously forecasted. That means more flares, more auroras, and more potential for disruption. Knowing this cycle helps governments and industries prepare for increased solar activity. For example, satellite operators can add extra shielding, and energy companies can protect transformers from potential overloads. It's a long game of watching patterns, and it's another reason why the sun is under constant surveillance. One of the most serious threats from solar storms is their impact on power grids. When a CME hits Earth, it induces currents in long conductors like power lines. These geomagnetically induced currents, GICs, can overload transformers, causing widespread outages and even permanent damage. In 1989, a geomagnetic storm caused by a CME knocked out power to millions in Quebec in just 90 seconds. And in 2003, storms forced grid operators across Europe to take emergency measures to avoid cascading failures. These events are not science fiction. They've already happened, and the risks are growing. NASA collaborates with the Department of Energy and utility companies to help prepare for worst-case scenarios. Monitoring the sun in real time allows power grid managers to reduce load, protect equipment, and minimize the impact of a geomagnetic storm. A single massive event could cause blackouts for weeks, which is why preparation begins with solar surveillance. With companies like SpaceX, Blue Origin, and Virgin Galactic entering the world of space tourism, solar activity becomes a direct safety concern for civilian travelers. Space tourists, unlike astronauts, may not be trained or equipped to handle emergencies in space. That makes it even more critical to avoid exposure to solar radiation from flares or CMEs. Short suborbital flights and orbital missions alike must be carefully scheduled during periods of low solar activity. If a solar event occurs mid-flight, passengers could be exposed to dangerous levels of radiation, and communications could be lost. That's a risk no company can afford.